Hello, and welcome to today's lesson. We're going to dive into an exciting area of geometry, focusing on how we manipulate shapes using space and movement, and how we describe this with numbers, specifically vectors. In this lesson, we'll be building on our existing knowledge and introducing the concept of vectors. We'll start by understanding what vectors are and how they describe movement in a plane. Next, we'll explore how to calculate the magnitude of a vector using Pythagoras' theorem. Finally, we'll work through some examples to solidify our understanding and see how vector transformations can be applied in various scenarios. With this strong foundation, we are ready to explore vectors. Vectors are a powerful tool in mathematics that allow us to succinctly describe movements and transformations. Imagine you need to move a shape from one position to another on a graph. Using vectors, we can not only describe the direction and distance of this movement, but also use this notation to perform and analyze more complex transformations efficiently. So let's dive in and see how vectors can make transforming shapes easier and more precise. Get ready to add this valuable technique to your mathematical toolkit. Let's get started. When we talk about moving a shape through space, we are referring to translations. To describe this movement precisely, both in direction and distance, we use vectors. A vector is a quantity that has both magnitude, or length, and direction. This means it tells us not just how far to move a shape, but also in which direction. Vectors are often denoted by a bold letter. For example, A. If we want to work with the vector in the opposite direction, we write it as -a. Let's make this more specific using proper notation. To clearly separate the direction and distance, we use column vectors. A column vector has two components, written as a equals x over y, where the top number x represents movement along the x-axis or horizontally, and the bottom number y represents movement along the y-axis or vertically. Think of this like rotated Cartesian coordinates, which you're already familiar with. For example, a equals 2 over 1 means we would move the shape by 2 units along the x-axis. As the number is positive, the shape must move to the right, but a negative top number would mean moving to the left. The bottom number is positive 1, and therefore we would move the shape by 1 unit up the y-axis. If the number was negative, we would move the shape downward. Column vectors give us both direction and magnitude, as each component tells us how much to move in a particular direction. Sometimes, we want to find just the distance of this movement, independent of direction. This is known as the magnitude of the vector. To find the magnitude of vector A, we use magnitude equals the square root of x squared plus y squared. This is derived from Pythagoras' theorem, considering the vector as the hypotenuse of a right-angled triangle. In this example, A equals 3 over 4. To find the magnitude of vector A, we can use our equation along with our x and y values. Using our x value 3 and our y value 4, we can calculate the square root of 3 squared plus 4 squared. 3 squared is 9 and 4 squared is 16. When we add these together, we can see that the magnitude of vector A equals the square root of 25, giving us a final magnitude value of 5. To move or translate a shape using vectors, you simply apply the same vector to each vertex or corner of the shape. Suppose we have a triangle with vertices at 1, 2, 3, 5, and 4, 3. If we want to translate this triangle by the vector 3 over 4, we would move each vertex of the triangle by 3 units to the right, and then 4 units upwards. Our new vertices would be 4, 6, 6, 9, and 7, 7. This method preserves the shape's size, angles, and overall structure, maintaining congruence. In today's lesson, we explored the concept of vectors and how they can be used to transform shapes within a plane. We began by defining what vectors are: mathematical objects that have both direction and magnitude, as well as how they are used to describe movement. We then introduced vector notation and specifically focused on column vectors, which succinctly describe movements along the x-axis and y-axis. By examining examples, we learned how to read and interpret these column vectors to understand specific movements, such as moving right or left and up or down. Next, we discussed how to find the magnitude of a vector, which tells us the total distance of the movement regardless of direction. This involved using the Pythagorean theorem to calculate the length of the vector. We also visualized vectors on a coordinate grid to see how they represent movements from one point to another. Finally, we applied our understanding of vectors to translate shapes. By using vectors, we can move every point of a shape consistently, allowing for precise transformations. This was demonstrated through examples where we translated the vertices of a shape using a given vector. Overall, vectors provide a powerful and efficient way to describe and perform translations in geometry, offering both clarity and precision in movements and transformations. By mastering the use of vectors, we enhance our ability to solve complex geometric problems and understand spatial relationships better.